This is the pre-lab lecture for Lab 3 of Electronics. We're looking at diodes today. And first off, the pre-lab, the first thing you're going to do is make up figure 1 in Circuit Lab. So you're going to simulate it. Then you're going to do a DC sweep where you change, a DC sweep will automatically change V1 from negative 15 volts to negative 14.99, etc., etc. And it'll do a DC analysis for each one of those points. And then the curve that you see is actually a composite of all of those individual DC analyses. And what you're looking for here is what is the diode current when the diode voltage is 0.7. Notice that the diode voltage is V1 minus V2, not V1. So we're not looking at where V1 is 0.7. We're looking at where this is 0.7. Let me show you what that looks like. So here is the circuit with a slightly different diode and slightly different resistor. And we're going to go simulate DC sweep. V1.V is our parameter we're changing, and we're doing linear from negative 15 to 15 by 0.1. And that's plenty close enough. And our two outputs are V1 minus V2 and I of D1. If you end up picking the cathode, you'll just get the negative of this current, and that's fine either way. Oops, so we have this, so let's run that DC sweep, and here you can see we've got the two curves. And as expected, when Vs is negative, we have no current, essentially no current flowing, and we have just negative Vs across the diode. In positive regions, then, we get about 0.7 across the diode, and we get increasing amounts of current. So this, even though it looks linear, is actually exponential. So let's zoom in on the positive range, and you notice it zooms both the top and the bottom when we do a zoom. So what we're looking for is when does this thing cross 700 millivolts. So let me zoom in maybe one more notch, and I'm looking at this top graph, and I'm looking for where it crosses 700 millivolts. 699.9 millivolts is close enough. That happens at a V1 of 8.1 volts. But what I really care about is VD and ID. So at VD of 0.7, ID is 2.357 milliamps. So that is your point that we asked you to take. And then what do you do with that? Well, we know we have this diode equation. ID is equal to IS times e to the VD over NVT. So we need to find VT. Well, that's not so bad because we know IS and N for our diode. So if we go back to Circuit Lab here and we double click on the component, we actually have model parameters for IS and N. So for your particular diode, the 1N4001, you can go look up what those are, and then you just solve this equation for VD of 0.7 and ID of whatever you found, and solve that for VT. Once you've found for VT, we have another equation. VT is KQ over T. Solve that for T, which is in Kelvin, and then convert that to Fahrenheit. So that's the pre-lab. Now let's turn to looking at a little bit of analysis of this circuit that we're playing with. And as you've learned in class, hopefully by now, the diode is pretty bossy. If it can turn on, it will. And if it turns on, it will take the 7/10 of a volt that it needs, and it will leave the rest for the resistor. So we know from a forward biased diode has this equation between, or this relationship between VD and ID. And we know for a resistor, you've got the Ohm's law relationship between VD and ID. So where will this circuit actually operate when you turn it on? Well, it operates when those two agree. So if I plot the load line, which is IR versus VD for a given VS, that gives me a nice line starting at 0. For 0 dV volts, then the entire VS is across the resistor, and it's a straight line all the way down to where the diode voltage is equal to Vs, and that intercepts at 0 current. Then we look at the diode equation, and you can see it goes up exponentially. So what happens? Well, these two are in series, so where the two currents are the same, that's where this thing is going to operate. So If I change VS, what happens? Well, this red line slides up on the left-hand side. The right-hand intercept stays the same place. So VS goes up, which means IR goes up for every VD. So this slides up. The intercept between these two then goes up somewhat. You notice that the VD is pretty much about the same. It's between 0.7 and 0.75 through this whole region. So your current will go up in the diode, but the voltage won't change all that much at a time. So this is called a load line analysis, and so what you're looking at is the IV relationships for the different pieces in your circuit. So what are we going to do in lab? Well, you're going to start off, as always, calibrating your probes. Then I asked you to experimentally find IS and N for your particular diode. So let's look at the diode. Let's look at a diode and see how we do that. So our diode that we have specified here is the BAV99. So let's look at the BAV99. There it is. And we click on datasheet. It takes us out to, let's choose a different one. That one doesn't seem to exist. So let's do the 5918 here and look at the datasheet for that one. Okay, so here's the datasheet for the 1N5819, and we'll go, and there's 3 different data sheets available. Let's look at the data sheet from Jamco, and you can see that this is a diode. It very crucially identifies how you tell what's the cathode and what's the anode. So there'll be a mark on the cathode of some sort. So it'll either be a painted line or it'll be a different colored plastic. So when you look at it, one end of the diode will always have a mark of some sort, and that will always be the cathode. So let's look at the maximum ratings. So this particular diode that I more or less randomly picked, you can see can handle up to 25 amps of forward surge current, so that's kind of a one-time thing. On an average basis, it can handle 1 amp of forward current. If we go down and look at the voltage at a current of 1 amp, it generates about a half a volt. Some of these data sheets have a maximum power rating, some do not. If you don't have a maximum power rating, then you can take the forward voltage multiplied by the average maximum current, and you can use that. So this thing can handle about a half a watt. So for your diode, you're going to go and look up these parameters. Notice that there's something that's not on here. There's no N or saturation current on here. There's no IS or N parameters. So that's why we're going to actually experimentally look at those. So how are we going to do that? Well, we're going to adjust V1 and get a couple of different data points on our curve. So we know that we have a diode curve, and we're going to measure a couple of data points, then we're going to use just mathematics to back those 2 parameters out. So just a reminder of how you measure voltage, current, and current. Voltage is measured in parallel with the component of interest. So to measure VD, you'll just take your DMM and put one probe on V1 and one probe on V2. And you'll do that for 2 different V1s. Doesn't really matter what they are. Then to measure current, what you have to do is you actually have to break this wire between the diode and the resistor, break that connection, and run that through your DMM in ammeter mode to come out. If you put the ammeter in parallel with D1, then all of your current's going to go through the ammeter and nothing through the diode, and you'll get numbers, but they won't mean anything. So you need to interrupt the circuit and put the ammeter in series with your current of interest. And then again, you'll do this for 2 different V's. Once you've done that, what do you do with it? Well, that we could maybe represent as, so here's one of my data points that I took, and here's the other data point that I took. And so I have VD and ID for those. So what do we know? Well, we know that this theoretical curve here follows this equation. And we know that if these points are on the line, that this is true for point 1 and this is true for point 2. So I have two equations and two unknowns. What do I not know? I don't know IS and I don't know N. We can assume VT is as we computed it in the prelab. So it'll be just over 25 millivolts. You can use the number that you used in the prelab if you like. So what do? Well, I want to solve these, so let me go ahead and divide the two equations, and that lets me cancel out IS, and the exponents of E subtract. Then I will solve this equation for N. So if you take the log of both sides and divide both sides by the log of I of d1 over d2, and then multiply by n to move it to the other side, you end up with this equation. So now I have all of the pieces that I need. I have VD1, I have VD2, I have VT, I have ID1 and ID2. So I can find n. Once I have n, I can go up to either of these two, it doesn't matter, and plug in n and solve that for IS. So that's how you're going to use your two data points to construct, to find IS and N so that you can write an equation for your diode. Now we want to compare the equation for your diode with the data that you take in lab. So how are you going to do that? Well, I went ahead and took 3 data points here just to see how well it extrapolated. Since I'm using 2 of these data points to find IS and N, those are going to match exactly. So I took a 3rd one just to see how well it did. So moving to MATLAB, how do we actually display this? Well, let's look at VDs from 0 out to 0.7, and I have the K, Q, and T from the prelab. I go ahead and compute VT, and this is a vector equation here now because VD is a vector. So I use the diode equation with my given IS and N that I computed in the prelab here that I've hidden from you, so you don't just copy mine, you do your own prelab. And I have a range of IDs. Now I want to plot them. So I take my experimental data. I have 3 points, 3 V measurements and 3 I measurements. And I go ahead and plot my diode curve using a straight line and my experimental data using a star. And that gets right to this plot. I give it a nice title, X label and Y label. And then I went ahead and put my IS and N right straight on my plot so I can see what it is. So that's how you do that in MATLAB, and I will be looking for a nice MATLAB plot for your data. There's one more thing in the experimental data we're going to look at. So instead of VS being a sine wave, we're going to reconstruct figure 1 with VS as a sine wave as opposed to a DC. So this is what we call a half-wave rectifier, and hopefully when you see the operation of that, you'll understand why it's got that name. The last thing that you're going to do is you're going to build figure 2, which is a full-wave rectifier, and plot N2 minus N1. So let me show you figure 2. So to plot N2 minus N1, we actually have to learn a little bit more about the scope. In the scope, we can plot N1 with respect to ground or N2 with respect to ground, and that will give us stuff, but really what we're interested in is N2 minus N1. Luckily, there's a math menu on the scope that you'll learn about. So if you hit math and set whichever channel N2 is on minus whatever channel N1 is on, you can plot the purple curve, which will be N2 minus N1. One thing I did forget to say is that back in figure 1, one of the things that we do ask you there is we ask you to compute what the maximum amount of, what the maximum voltage source can be so that you don't fry your components. Well, from the data sheet, you know how much power D1 can dissipate. All of our resistors up there are quarter-watt resistors, so you know R1 is a quarter-watt resistor. So from the data sheet, you can figure out what the maximum amount of current through D1 is. From your power equation, you can figure out the maximum amount through R1. Whichever of those two is lower is your maximum safe current. Once you have the maximum safe current, then you can find the maximum V2. You can use the constant voltage drop model and just add 0.7 to get the maximum V1, which is your maximum power supply. So we're really asking, how high can you turn this up before one of these two things fries? So that's part of your post-lab that we'll be looking for. Hopefully this has helped you and you're ready to dig in and learn a little bit about diodes.